without further ado, it's a pleasure to have Kevin Walker telling us about universal state sums.
Good, thanks, Chris. Yeah, please let me know if I'm mumbling or not talking loud enough or anything like that. And I'm always happy to be interrupted by questions. So what's a state sum? Here's, some things that have been published about them. The earliest one I'm aware of is something that Kaufman did in 1982 that computed the Alexander-Conway polynomial. But I am certainly not an expert on the history of the subject, and I just saw that David Yetter in the chat, there was something else I could have included here. So see the chat for David's thing. What I want to do is write down a formula for a general and category that specializes to the things listed here, actually not the first one, but the others. Okay, so what do I mean by a state sum? The rough idea is we give some combinatorial description of n plus one dimensional manifold. It can be like a triangulation or a handle decomposition. And then we have some set of labelings or states, hence the name state sum. And then given a state, we can compute a bunch of local weights, maybe like for each simplex, for each handle. And then we sum over all the labelings, and we take the product over all the local weights, add those up, and we get some number, z, and then we hope it's independent of the combinatorial description of our manifold. And this can also be interpreted as some kind of tensorial contraction, pretty much in tensors together. So what is it? We expect that a TQFT, we might be able to compute it this way because we could, if we have a TQFT, we can cut our n plus one manifold W up into small pieces. And then as we reassemble the pieces, that's kind of like doing a tensorial contraction, and hence we get a state sum. But the details of carrying this out have, we've got corners and things like that to worry about. So that's why, I guess it makes the subject a little more interesting. Okay, so without further ado, here is like universal state sum. It'll take me a few slides to explain what this means, but it's almost all of it is very simple and something you probably would have guessed yourself if you're at all familiar with these other state sum invariants. Okay, so what is W? W is an n plus one dimensional, I'm calling it an H manifold, where H means it could be an oriented or unoriented manifold or spin or pin. I just want to treat all those cases simultaneously. And then we have a handle or cell decomposition of W. And then we also need to choose some in category C. And it has a list of things it has to satisfy, and I'll talk about those in more detail in a moment, but just very briefly for the experts. I want it to be H pivotal, so when H is SO2, that just means the usual pivotal, like a pivotal tensor category, and it should be K linear. It's got a conjugation map. If you're used to like ribbon categories, that involves like reversing the arrows in your diagram. The biggest conditions, the ones that are hard to satisfy, it should have finiteness and simplicity properties. Again, I'll say more about those in a moment. And then finally, it needs some kind of evaluation map. The evaluation map takes a string diagram on the n sphere and evaluates it to some number in our field, K. And we want this evaluation map to give non-degenerate pairings for n morphisms. Given two n morphisms, we can glue them together, get a diagram on the n sphere and evaluate. And we want that to be non-degenerate. Okay, so continuing to explain what the symbols in this formula mean. Curly L of H is a set of labelings of the handle decomposition. And what we want to do is label an I handle of H with a minimal n plus 1 minus I morphism. So handles get labeled by morphisms, and there's a degrees get reversed. And it should be compatible with the adjacent handles that are of higher index. So first we would label all the in handles with the zero morphisms of our category, and then we would label the, the n+1 handles get labeled by zero morphisms, the n handles get labeled by one morphisms, connecting the two zero morphisms on either side, and so on. And we'll see lots of examples of this later in the talk. Okay, what do I mean by minimal? Given some morphism y, we can take an iterated identity of y until we're close to the top level of the category. And then this thing is going to be some kind of algebra, a commutative algebra, unless k is equal to n-1. And it's, we're assuming semi-simple. And so, but I want to, I'll call y minimal if it turns out to be a simple algebra. So it's as small as it can be. And then I'm going to assume that my category, that any k-morphism is a sum of these minimal k-morphisms. So one example of this is, an object in a tensor category is a isomorphic direct sum of simple objects. This condition about this sort of a completeness, or I'll call it a weak completeness thing, is actually, it's just technically convenient. I could drop that assumption and then the formula would just look, I'd have to insert a bunch of idempotents into the formula, but we can always take any category and weakly complete it. And then there's an equivalence relation on idempotents where if you can express one in terms of another by circling them, but let's not worry too much about that. Okay, what about this thing? Well, given a handle H, we can look at its boundary and then the various cells of the cell decomposition. So I'm thinking of the cell decomposition and handle decomposition at the same time. The handles are just the thickened cells, and the cells are just the cores of the handles. And so I can look at how those handle cores or the cells intersect the boundary of the given handle. And that gives me a cell complex, but now because of these labelings, I can turn that cell complex into a labeled cell complex. In other words, a string diagram. I call that beta of the boundary of H. And then I can evaluate it because I assumed I have this evaluation map. The boundary of a handle is an n sphere. So, okay, so everything I've said so far is, I think, something you would guess if you were familiar with the literature on state sums. So what I'm going to say next is the kind of the only interesting thing, maybe almost the only interesting thing. I'm going to define a number for every k-morphism x. I'm going to call it the norm for lack of a better name, but if someone else has a different idea of what it should be called, let me know. And it's defined inductively. I look at all the k+1 morphisms from x to x, and I sum over the minimal ones, or more precisely, the equivalence class of minimal ones. And then for each minimal morphism y, I have this quantity I call trace, which I'll define in a moment, and I square it, and then I divide by the norm of y. So it's an inductive definition. To get the induction started, if k is an n morphism, then the norm, remember, we've got an inner product on n morphisms, and I just take the square of that inner product. Okay, what's this trace? You can think of the trace as like we've got a way of evaluating n-dimensional pictures on the n-sphere, n-dimensional string diagrams. And if I've got a k-morphism y, I'd like to turn it into some n-dimensional diagram so that I can assign a number to it. And so this is, in some sense, the simplest way to do it. First, I take y and I take a product with a sphere, so it gives me some higher dimensional string diagram. And then I take some diagram on the ball, boundary of y, and close it up. So this might look kind of complicated, but it's the obvious way of turning I guess in this case, a k+1 morphism into a string diagram on the n-sphere. And we'll see some examples below. Okay, so I promised more details on N categories. So what do I mean by H pivotal? Morally what I mean is that I impose enough conditions on my categories such that string diagrams on H manifolds make sense. So morphisms should have adjoints, and in terms of this Lurie point of view, this is roughly what you would call an H fixed point, H n-dimensional fixed point, not H n+1. And I'm using a strict version, though probably this could be generalized to a non-strict version. So as I said, for a tensor category, this is just the usual sense of pivotal. If it's a braided category, then it means a ribbon. So my finite and semi-simple, I want all these scheme module spaces. I'll define those later. But they should be finite dimensional. And when I form categories for n-1 manifolds, I want them to be semi-simple for all manifolds of I and all boundary conditions C. So probably these hypotheses could be weakened a bit. Like I think probably I just need them when these manifolds are of the form sphere across ball. But just to be safe, let me make the stronger assumptions. Conjugation. That should be thought of as my N manifolds, the things I'm drawing string diagrams on, should probably be thought of as having an extra sort of time direction and an H structure on that. And this conjugation map involves reversing the time direction. So this is familiar from things like rep Q of G or other tensor categories. If I've got this morphism X, there's this sort of reflective version of X where I reverse the arrows and you can glue X to its reflection to get a diagram on a sphere. You can think of conjugating something you can also think of as turning it from an incoming to outgoing.
Kevin, can I just ask about this pivotality condition?
Sure.
So say we're in 2+1 dimensions.
Mm-hmm.
Is this an SO2 or an SO3 fixed point condition?
That's SO2.
Okay, that's what I thought. I just wanted to be sure. So anything beyond that we think we need is going to come from other conditions.
Yeah, like in particular these conditions.
Yeah, perfect. That's what I thought.
Yep. Yeah, no, thanks for the question. And again, I'm assuming, I'm making very strong duality assumptions all the way up to, but not including the top dimension. And then in some sense, the arguments we're making is about extending things from dimension n to dimension n-1, or n+1. Okay, and then finally, I didn't write it explicitly, but I have this evaluation map, and given the evaluation map, I can take N morphisms or string diagrams on the N ball with some fixed boundary C, and I can pair the two together and evaluate and get a pairing like this, and I want that to be non-degenerate, and this is for all C. Okay, so what kind of categories meet all those requirements? So I'm going to distinguish between this first condition, just the H pivotality and everything else. This is sort of easier to satisfy. So things that are H pivotal, I'm going to assume H is SO, a pivotal tensor category, as I said, or 2 category in dimension 3 ribbon categories, rep Q of G with Q generic. So 3 category, you can make it of contact structures on 3 manifolds. In dimension 4, an example would be the contact category that Paul talked about a couple of weeks ago in the seminar. In arbitrary dimensions, I can take pi less than or equal to n of any space, any target space. This will have all the duality assumptions I need. I could take a symmetric monoidal category that has duals. I'm calling it a symmetric monoidal ribbon category. I don't know if that's standard terminology, and turn that into an N category. And then in general, there's a paper that Scott Morrison and I wrote talk about this your disk-like category. So any of those will do. So now for the finiteness and semi-simple, all the other conditions, we find in dimension 2, the things that work are fusion category. What's called a subfactor planar algebra. So it's a 2 category with 2 objects and some positivity properties. A multi-fusion category works. Of course, we can write those as direct sums of, or it's Morita equivalent to the sums of fusion categories. In dimension 3, a premodular category is good input data. Or this fusion 2 categories, which David Reuter talked about, I think it was just last week. That works as an input. I don't know any examples in 4+1 dimensions other than the ones that work in any dimension. So if I take pi less than or equal to n, but this time not of any space, but of a space which has finite homotopy groups, that will work. I could also consider, a special case of that would be, dual to a special case of that would be the ribbon category rep G, where G is a finite group. Okay. I promised you examples of what I mean by trace. The S is for sphere. Let me call it the sphere trace of S. Again, I'm open to better names. But in the n equals 2 case, for a zeromorphism, it's the evaluation of the empty picture labeled by X. So in some 2 category, we have multiple zeromorphisms X, and we color the 2 sphere with X, and then we evaluate. That's some number, and that's what I mean by the trace. If it's a 1 morphism, then it's just the quantum dimension of S. We draw a loop on the 2 sphere and labeled by X. There could be some ambiguity here if we're in a 2 category and the left quantum dimension might not be the same as the right quantum dimension. So I'm assuming a tensor category, not a 2 category there. And if we just have some arbitrary 2 morphism, we take the 2 morphism, looks kind of like that, some coupon, and then we take the conjugated coupon and we glue them together, and we get sort of the inner product of X with itself. If we're in a 3 category, and I guess I'm thinking of the case of like a fusion 2 category as Chris and David have defined. So that's think of it as a 3 category with 1 object. For k equals 0, again, I just evaluate the empty picture, this time on the 3 sphere. For k equals 1, I can take a 2 sphere and label it by the 1 morphism X. So evaluation of a 2 sphere labeled by X. For a 2 morphism, is I think of, identify it with some 2-dimensional picture like this. So here's my 2 morphism alpha. And then I want to cross this with a circle to get some solid torus, and then I want to glue it together with some other torus. And if you do that, I'm kind of bad at drawing it, but it's kind of like, in this case, it would be 3 disks with their boundary identified. So it's like taking this theta graph and spinning it around. So this would be like 1 disk, 2 disks, 3 disks. And finally, if we have a 3 morphism, say the boundary is tetrahedral, then this will be, it's a picture similar to this, but in higher dimensions, sort of a double cone on a tetrahedron. Okay, and finally, norms. We've got this inductive formula. So let's just say what it works out to be. If we're in the top dimension, as I mentioned before, it's the square, sort of the square of the norm squared of X. We take X, we glue it to its conjugate, we evaluate, and then we square that. When we've got an n-1 morphism, so we're 1 below the top dimension, then it's the dimension of the endomorphism algebra of X. So this is typically 1, but if we're doing fermionic versions of things, it might be 2 if we've got like a Majorana simple object. When n is equal to k minus 2, so then in this case, the endomorphisms of X are a tensor category, and it's the global dimension of that tensor category. And in the super case, we have to divide by the norm of Y. And probably, I should say, and then multiplied by the evaluation of the two sphere. That's kind of a technicality. And then finally, when k is equal to n minus 3, we look at x. The endomorphisms of x are some kind of multi-fusion category. And I'm going to sum over minimal endomorphisms, which is like summing over the blocks of that thing, and I take the reciprocals of all the global dimensions. So this quantity also appears in Douglas and Reuter's work, and so I guess I want to say, if you think about 3 categories or braided categories, this is an important number because it's a close cousin of the global dimension, which we know is an important number.
Kevin, sorry, this is Victor Ostrik. Stop you for a moment. So this formula they involve the denominators. Should I worry that denominators would be 0 sometime, or?
Yeah, well, I think my assumption is that the denominators are not 0. So that
So it's just my assumption.
But certainly you could find examples which satisfy a lot of the conditions I'm putting on, but maybe the global dimension turns out to be 0, and that would fit. Some of my hypotheses fail in that case. But I think it is interesting I'm sort of concentrating on the easiest case in this talk, and I think it is interesting to think about pushing it out more generally. Okay, so what I want to do next is show an example of.
Can I ask a question?
Yeah.
There's something that we also found curious in our work is that in this dimension, for k equal n minus 3, this global dimension does not depend on, say, the monoidal structure. So this just depends on sort of the underlying, in the 3 plus 1 dimensional case, just depends on the underlying 2 category. So that's something that one can just see. Is there some good explanation from this perspective why this is?
Let me think a moment. Not off the top of my head. Good question. I can try it again to answer it later, but
okay.
I think right now.
Thanks.
Okay, so for the rest of the talk, what I want to do is give some examples of how this, general formula specializes to familiar ones. And then I want to sketch the proof that this is in fact independent of the handle decomposition, and then give a few more examples if there's time. So first example we want to look at is Tarai-Vero, sort of prototypical state sum. So I had this formula, let me bring it back briefly. So we've got sum over labelings, and then for each handle, we've got this evaluation on the boundary of the handle, and then with this norm factor. So I want to look at what these 3 things are in lots of different examples, starting with Tarai-Vero. So I made a table. The 0 handles don't get labeled. They're too small. The 3 handle gets labeled by the unique object in my fusion category that I'm taking as input. The 2 handles are labeled by simple objects. Those are the minimal 1 morphisms. The 1 handles get labeled, I should have said this above, but I forgot. When you get to this dimension by minimal object, I just mean choose a basis. So near the 1 handle, and we're assuming a generic cell decomposition, so it's got 2 handles coming in, each of which is labeled by a simple object, and so this alpha, the labels for the 1 handle, will run through some basis of that. Okay, so now I look at the boundaries of the handles. The boundary of a 3 handle is a 2 sphere labeled by the empty set, and that evaluates to 1. I'm just choosing that evaluation map. On the boundary of a 2 handle, I see a single loop that evaluates to the quantum dimension. On the boundary of a 1 handle, I see the theta graph, and let me draw that just in case it's not clear. So here's a 1 handle, sort of a disk across an interval. And then it's got 3 two handles attached along these, coming in. And these would each be labeled by some simple object A, B, and C. And then where it intersects the 0 handle, I have this sort of trivalent vertex, and then I've got another one going on the back here. And so if we unwrap that, this looks like a theta graph. So here's the handle, and I have just that graph. And then finally, at the 0 morphisms, we have this tetrahedral thing. And so this tetrahedral graph can be turned into a labeled string diagram, taking labels like this and this. And then the norms from the table above, the norm here is 1, just by convention. It's, here we have the norm squared, so theta squared. The endomorphism algebra of a simple object is 1, so that's 1. And then here we put the global dimension. Then putting it all together, this is plugging into the general formula, we get this, which is recognizably the Tarai-Vero state sum. We could do it again for a general cell decomposition and not a generic one. So now generic means dual to a triangulation. And that's how Tarai-Vero was originally defined, but there's really no need to restrict to triangulations or Poincare duals of triangulations. So these 2 columns look the same as before, but now we have any number of 2 handles running over a 1 handle, and so we get this what I call a mutant theta graph. Just evaluate that thing. And then the link of a vertex could be anything. It might be a cube, tetrahedron. Here's a triangular prism. And again, the formula looks very similar. These parts are exactly the same as before. We replace the thetas by these mutant thetas, and we replace the tetrahedral symbols with just whatever the length of that 0 handle happens to be. Okay, Crane-Yutter state sum. Here the input is a pre-modular category. So you can think of it as a finite semi-simple 3 category with trivial 0 and 1 morphisms. And I'm going to assume a generic cell decomposition. The labels for, there's only 1 label for a 4 handle. The unique 0 morphism for 3 handles are labeled by the unique 1 morphism in our category. 2 handles, again, labeled by simple objects. 1 handle is labeled by endomorphisms. And now we have, over 1 handle, in this dimension, we have 4 2 handles going along the 1 handle in a tetrahedral pattern. In the original Crane-Yutter state sum, this 4-valent vertex was resolved into 2 3-valent vertices, but I'm not going to do that. Then for the evaluation on the boundary of the handles, we get various things. This should be thought of as the 1 skeleton of the cone, double cone of a tetrahedron. This is the 1 skeleton of a 4 simplex. These terms here are similar to Tarai-Vero, but then we get this new one, this inverse of the global dimension, which is a special case of that sum of the reciprocals of the global dimension that I showed before. And we plug it in, and up to this issue of resolving these vertices, this is, again, recognizably the same as the original Crane-Yutter state sum. But we don't have to assume a generic cell decomposition. And one interesting thing to do is to take our cell decomposition to be just a 0 handle with a bunch of 2 handles. So I'm thinking this is describing a 4 manifold, not a 3 manifold. My input is a pre-modular category C. So the attachment map for these 2 handles is some framed link in S3. So now I draw out the table, now with only columns labeled by 0 and 2, because I only have 0 and 2 handles. 2 handles, again, they get labeled by simple objects. What you see on the boundary of the 0 handle is this framed linked L, and the evaluation of that is just the generalized Jones polynomial for L with labels on the strands given by beta. So this is a generalized Jones polynomial. On the boundary of the 2 handles, we just see a simple loop. So again, we just get this quantum dimension. The norms in both cases are 1. And plugging it into the general formula, we see that we sum overall labelings of the Jones polynomial times these quantum dimensions. And this is just the up to a normalization. This is the Reshetik and Duraev-Dane surgery formula. And if, as we all know by now, if C were a modular category, not a pre-modular category, then this answer we compute would depend only on the boundary of W and not the interior. Okay, one more example before we get to the proof. The Douglas-Reuter state sum. So the input is a fusion 2 category. And Chris or Dave, you should jump in if I say something wrong, because I haven't actually read your paper. I've only heard your explanations of it, so I might have some details wrong. I want to take a generic cell decomposition, but now there are more things to label. The 4 handles, there's only one choice, because of the type of category we're using. It's only got a single zeromorphism. The 3 handles get labeled. They have to be labeled by 1 morphisms, and I think one of the key insights of this work, and also in Douglas and Reuter, is we should be summing over the minimal 1 morphisms. And if our category doesn't have minimal 1 morphisms, then we need to complete it so that it does have them. And we'll see the reason for this coming up when I sketch the proof. 2 handles are labeled by 2 morphisms, and 1 handles by 3 morphisms, which has kind of a tetrahedral pattern on the outside. This should be thought of as the cone on the one skeleton of a tetrahedron. Okay, so now we have to evaluate boundaries of handles. For the 3 handles, we get this 2-sphere labeled by the minimal object M. For the 2 handles, we get the spun theta graph that I defined before. For the 1 handles, we get a double cone on a tetrahedron. This should be thought of as a single cone on a tetrahedron, so we just glue 2 of these together. I have not attempted to draw it. And on the 0 handles, we see the boundary of a 4-simplex, which is also what we saw in Crane-Yetter, except this time we're considering the 2 skeleton of the boundary of a 4-simplex, not just the 1 skeleton. The norms are as before. Here we take a global dimension of the tensor category corresponding to M, and we also have to multiply by the square of the 2-sphere evaluation for M. And then the factor for the 4 handle is the sum of the reciprocals of the global dimensions, which I'm calling GD sub 3 of C, and then we write it out. And I believe, the notation is different, but I think this is exactly what Douglas and Reuter wrote down. I will note, though, that I could have done this with a non-generic cell decomposition, so it doesn't have to be dual to a triangulation. Okay, let me pause and invite more questions before I dive into sketching the proof. Okay. So the outline for the proof is this H pivotality allows us to very easily construct an n plus epsilon dimensional TQ of T. So all the constructions you do will be in the context of that, though in some sense I'm just using the top 2 levels of this TQ of T, the vector space and 1 categories. And then we can try to do an inductive construction of the path integral to sort of complete this TQ of T to one that's n plus 1 dimensional. If we start out knowing the path integral of a K-sphere thickened up, and that gives us a pairing on the scheme module of a thickened K-sphere, and then we get a co-pairing on that, and then we can use that to compute a thickened K plus 1 sphere. So we've made our way from K spheres to K plus 1 spheres, and we just start at 0 spheres and work our way all the way up. So this is the core of the proof. Once we've done that, we can compute the path integral for an n plus 1 manifold in terms of a handle decomposition, and then another key step in the proof is that the gluing formula we write down is associative, and that allows us to see that this is independent of handle decomposition. And then we can just reinterpret this computation as a state sum. Okay, so what do I mean by this in plus epsilon dimensional TQ of T? My input is an H pivotal in category, which means that I have a good theory of string diagrams on N manifolds. So this notation, if I've got some K-dimensional manifold, I mean C string diagrams on K. So it's all by string diagram, of course, the codimension 0 cells are labeled by zeromorphisms. In general, the codimension J morphisms are labeled by, or codimension J strata are labeled by J morphisms. Then I can form this generalized skein module where I take finite linear combinations of string diagrams and I mod out by local relations. That's what I associate to an N manifold. To an N-1 manifold, I can associate one category whose zero morphisms are just string diagrams, and the one morphisms is skein module that I just defined before. If I've got an N-2 manifold, then I can define a 2 category where the 0 and 1 manifold, 0 and 1 morphisms are just string diagrams, and the top dimensional morphisms are skein pictures where we linearize and mod up by local relations. And in general, we can construct a K category this way. It's actually only these pieces that concern us in the talk. But I do want to point out that, that this is somehow fully extended. We can construct invariants all the way down to points. Okay, so for a path interval, what do we want? Well, we want it to be a function on the skein module of the boundary of the N+1 manifold W. So it sees a skein and it spits out a number. And in particular, we can look at the path integral for M cross I and use that to construct a pairing on N manifolds. And if you want a fully defined TQFT, this had better be a non-degenerate pairing. So I'm not making assertions here. I'm just sort of, these are the things we're going to try to construct. And non-degenerate implies we have a co-pairing. And then once we have that co-pairing, we can define a gluing formula for N manifolds. So I've got a manifold W chopped into pieces W1 and W2. And then W is something that takes skein pictures on these 2 pieces of the boundary and gives a number. And then you just, to define it in terms of the path integral of the individual pieces, we stick the co-pairing for this manifold M0, which occurs in the middle. So this might look a little bit complicated, but it's the only reasonable thing to write down. And just to put this in a very computational explicit form, if I've got an orthogonal basis of this manifold that I'm gluing along, say EI and EI bar, then you'd say that, here's the path integral we're trying to evaluate. So I put some boundary condition consisting of X1 and X2. On the X1 lives here, X2 lives over there. When I chop the manifold apart, I have these new boundaries, so I plug in my elements of my dual orthogonal basis. But I need the sort of scalars that has come as part of the co-pairing, and if it was an orthogonal basis, then it's just 1 over the norm squared of these guys. So yeah, these things better turn out not to be 0, or the whole construction stops. Okay. So some terminology at an M, K handle body is an M-dimensional manifold built out of handles of index K or less. So now, maybe this is too much detail, but let me outline the inductive part of the proof. We assume that we've constructed a path integral for all M+1 dimensional manifolds built out of K handles or lower handle index. And that we've shown that this is invariant under handle slides and index less than or equal to K handle cancellations. So that isn't quite the same as saying it depends only under manifold W unless or that won't be true until we hit the very top dimension. And then we're also assuming inductively that we've constructed pairings for n-dimensional manifolds built out of K handles. And so we need to start the induction and then describe the inductive step. To start the induction, we just assume that we've got this evaluation map, and as I've said several times, I'm just assuming that it gives non-degenerate pairings so that we satisfy this condition. So we just going to, this assumption when K equals 0 is built into our requirements for our input data, the N category. For the inductive step, trying to go from K to K plus 1, we're trying to compute, first thing we would like to do is compute the path integral of a thickened K plus 1 sphere. So we chop the K plus 1 sphere into two pieces. And we note that the thing we're gluing along is a K sphere. And so that's what makes the induction work, because by our inductive hypotheses, we already know the path integral of this manifold thickened up, which means we know the inner product for this n-dimensional manifold, which means we know the copairing, which means we can plug it into the gluing formula. And that's exactly what we do here. So this is just a special case of the general gluing formula I wrote before. Each of these pieces is just some big n plus 1 dimensional ball. I evaluated on the original boundary condition on B prime or B double prime, and then some basis that I'm plugging in these places. And then I normalize by inner product of the basis vectors. So let's look at a special case where the boundary condition B has a spherical symmetry. It's some n minus K minus 1 morphism C cross a K plus 1 sphere. In that case, and this is the other important observation, is that we can take our orthogonal basis to be minimal the sphere labeled by minimal morphisms. So this is one of the few new ingredients in the talk, I think. And then once we do that, we can rewrite the sum as the path integral of this n plus 1 dimensional ball, which is this piece right here. And then it's the minimal guy. Actually, I should have written a product with a sphere there. There's a typo. But this numerator is just two copies of what I was calling the sphere trace. And then the denominator is, again, there should be, let me try to correct it. Should be cross a sphere in all of these cases. And you may recall from far above that I have this mysterious quantity called the norm, which in some cases yielded a dimension of an endomorphism algebra, in some cases gave the global dimension of a tensor category. So where did that formula come from? Well, it's exactly the formula for an inner product of of a K plus 1. Anyway, product of a morphism of the sphere with itself. And so this inductive formula, which comes from applying the TKFT gluing formula, exactly matches the formula we wrote down far above. Let's see, this one. And that's where this comes. Okay, so now once we've done that, once we've learned how to bootstrap knowing the path integral of just a ball to a path integral of sphere across ball, that allows us to write down a formula for a n plus 1 dimensional manifold that has a handle body decomposition, so long as the handle's indices never get above K plus 1. And we'd like to know, is that independent of the handle decomposition? Well, handle decompositions are related by handle slides and handle cancellations. The invariance under handle slices is trivial because that is just diffeomorphisms of the boundary. So that this part is very easy. So the key step is it's showing that the things we've written down so far satisfy a handle cancellation. So here's a manifold I start with, plus one dimensional, I add a K handle, and then later I add a K plus one handle, and is that the same as just doing nothing? This is what we have to prove. So observe that if we start with W, which has changed colors mysteriously, from one slide to the next, here's adding the K handle and later adding the K plus one handle and later adding the K handle. But suppose we added the handles in the other order. First add the, perversely, we first add the K handle and K plus one, excuse me, I've got these reversed, oops. And then add the K plus one handle. Well, each of these things is equivalent to just adding a boundary collar. And it's easy to see from the gluing morphism that adding boundary collars doesn't do anything. So if this diagram commutes, if going this direction is the same as going that direction, then we've proved candidate cancellation. And to show that this diagram commutes just means if we've got a n plus one dimensional manifold divided into three pieces, then we can glue them in any order we want to. So here's, the punchline is that associativity of the gluing formula implies invariance with respect to handle cancellations. Okay, so what we've proved so far is that, and this is actually kind of an old result, if we've got an N category that's satisfying A through D above, which we call as some kind of pivotality, finite dimensionality, semi-simplicity, and non-degenerate evaluation map, then we've got an easy construction of an n plus epsilon dimensional TQFT, and that extends uniquely to a full n plus one dimensional TQFT, fully extended, with the path integral of the n plus one ball being the evaluation map that we supplied as part of the input data. So the proof that I just sketched of this theorem gives us what one might call an algorithm for computing the path integral of an n plus one dimensional thing, but it's not very explicit because of various times I just say choose bases. So to get something that looks more like a state sum or a formula rather than an algorithm, we have to observe that we can take as our orthogonal basis these minimal J morphisms. And so the state sum formula follows easily from this if we combine it with the idea of using minimal morphisms as a basis of the space. Okay, so far I've only used the general state sum to reconstruct things that were already known. So I want to give some examples that are a little more exotic. So the next example would have been exotic like 6 or 7 years ago, but it isn't anymore. But we can.
So Kevin, I think you maybe essentially just said this, but just to make sure, the thing that wasn't present in your earlier view of how to extend 10 plus one dimensional theories was kind of how to turn it into a formula by picking these minimal representatives at every level. Is that a fair summary?
Yes, that's a fair summary. And more precisely, I guess I thought it would just be too difficult and messy to turn it into a formula, and then eventually got around to trying to do it in the 3 plus 1 dimensional case. And then I discovered that you and Dave had already done that like a year earlier. So then, that motivated me to try to do the general. I guess I realized that doing 3 is a large number. So if you can do 3 plus 1 dimensions, you can probably do n plus 1. So.
Great.
But I would have been satisfied just to go to 3 plus 1 were it not for your paper. So thank you for motivating.
Can I ask a question about this minimal chain morphisms here?
Well,
so you would pick, if you have two of these chain morphisms and there is a non-zero J plus 1 morphism between them, then you wouldn't think of them as being orthogonal. So you pick like one of them in each sort of plot in some sense. Is that?
Yes, that's exactly true, and that is important. And I think maybe this slide, I, in very sketchy form, sketch the equivalence relation. But
I see. Right. Okay. Exactly. Okay.
But I should have. I was, if I had time to do a second version of these slides, I would have put more emphasis on that fact. So thanks for asking the question. Okay, so let's do a few more examples that are a little bit less familiar. I think by now it's well known. In fact, this morning I discovered a paper by Arun Debray and Sam Gunningham that I was not aware of. But I think various people have constructed a 1 plus 1 dimensional pin minus TQ of T, taking as the input one, super one category, Cliff 1, complex Clifford algebra, which has an odd generator S, which squares to 1, and they give it the pin minus structure. If we reflect it, then we get multiplies by a fourth root of unity. So now we draw the familiar table for the state sum. The label, we've only got one choice. There's a unique zero morphism in this category. So the only thing that's really getting labeled are the one cells or one handles, and they get labeled by either the identity or by this odd generator S. And now I should have said, just to give me more flexibility, I want the evaluation map of the empty picture to be some scalar lambda. Oh, yeah, I wrote it up here. So in previous slides, I was writing 1 here, but now I'm writing lambda. Evaluation of the empty picture is lambda by definition. One can check, that the inner product of either of these guys with itself is lambda, as we see on the boundary of the one handles. But on the boundary of a zero handle, we have multiple one handles coming in, and each of them may or may not be labeled by S. So what we see is somehow a disk, and then here's all the one handles coming in. Each one handle optionally has a dot labeled by S. So what we see is a circle. That's our in-sphere, is a circle with some number of dots. And so that evaluates, if we multiply S's together, first it might seem like we just get 1, but remember that we need sort of a spin, we need to keep track of spin frames. And so each of these handles has a standard spin structure, but one handle could be some arbitrary spin diffeomorphism of the interval, which could introduce a factor of this reflection of the interval, which would give us this fourth root of unity. So that means it evaluates to lambda, that's the basic disk value, times some alpha raised to some power, or it might be 0 if we had an odd number of dots. And then the normalization factors are 1 or lambda squared, or 2 actually in this case, because the unique idempotent in this category is a Majorana thing. So the dimension of this endomorphism algebra is 2. State sum, once we've pulled the lambdas through, we get lambda raised to the Euler characteristic. We get a sum over labelings of these factors, so some fourth root of unity. And then we take a product over 2 handles of just 1/2. That's reciprocal of this number. But we can rearrange it. We just note that this sum is going to be 0 unless the one handles that have the dot on them, that have the odd label, form a 1 cycle. So now we can rewrite it as a sum over 1 cycles of some fourth root of unity. And we've pulled out this factor of 2 to the number of 2 handles. And then one can check that this exponent lines up with, say, if you look at, say, the paper of Kirby and Taylor, at this point, we're getting very close to how the official definition of the Brown-Arfin variant. And so we end up with some scalar depending on Betty numbers and the Euler characteristic times an 8th root of unity raised to the Brown-Arfin variant. Finally, last example, to do something truly new, we could try to do a fermionic version of the Tarai-Vero state sum. So the input's going to be some kind of superfusion category. Give some examples in a moment. And so here's a table that we drew for the Tarai-Vero state sum, and in purple or whatever this color is, pink maybe. I've shown that the changes to the usual non-super case. So one change is, when we define the global dimension, of course, we need to divide by the norm of, if it's a Majorana object, we divide by 2 at some end. These simple objects might be Majorana objects. The norm of a simple object might be 2 if it's Majorana. When we draw pictures like this, we have, we might have odd morphisms. These are somehow super vector spaces that we're plugging in at the vertices. So I wish I had fully worked this out and could say things more precise, but let me just sort of, make some guesses or give some general ideas about what this fermionic version looks like. It will look a lot like the original Tarai-Vero section, except we're going to be keeping track of some odd degrees of freedom, which means that we're going to need to be keeping track of some spin structure data very similar to the way we did in this Brown-Arts state sum. So in some sense, this is a warm-up for the 2 plus 1 dimensional case. So what are the simplest examples of superfusion categories? Well, we might look for examples that have only a single non-trivial object. So they'll be generated either by 1 and an ordinary object, which I'm calling X, or 1 and a Majorana object, which I'm calling M. And I guess I'm aware of 3 examples. I don't know if this is all of them. My guess is that it is, but I certainly have not proved that. One is something I call C2. You can think of it as the Ising TQFT modulo a fermion. And here are the fusion rules of your Majorana object tensor with itself is 2 copies, 1 even, 1 odd of the tensor unit. And the principal graph of this category looks like this C2 Dynkin diagram, hence the name. Another example comes from SO3 level 6, and again, we mod out by a fermion. All these examples are produced from fermion condensation. Here we have an ordinary object, X, and its fusion rules are X tensor X is a tensor unit, and again, then 2 copies, 1 even, 1 odd of X again. Principal graph looks like this, where I've drawn in red a sort of an odd edge of the principal graph, corresponding to that odd dimension there. And finally, we can take half of E6 and mod out by, again, turns out to be a fermion in the Drimfeld center, so this is a little more sophisticated construction. We get a single Majorana object in addition to the tensor unit, and its fusion rules are 2 copies of the tensor unit and 2 copies of M. Principal graph looks like that. And now let's observe. I've not worked out state sums with these categories, but we know that if we know what the Hilbert space is for a 2 manifold, so this is string diagrams drawn on the spin 2 manifold, drawn with this superfusion category, modular relations, and it's going to be some super vector space with super dimension P/Q. Then if we take the 3 manifold obtained by crossing with a circle with the bounding spin structure, the invariant is going to be P plus Q. It's the total dimension. And if we take the non-bounding spin structure on the circle, we get P minus Q. So this gives us some hints about what the state sum should work out to be for some manifolds at least. And it turns out these dimensions can be calculated via a sort of super Philinda formula. So here's a table of dimensions for these 3 examples. We get all these big numbers. I'm just backing up. What will the summation look like for these theories? Well, we've only got a single, so this column tells us how we have to label when we're doing the state sum. And in the examples I gave, we only have 1 non-trivial object. So we're going to be summing over subsets of 2 cells. And then the way those two cells can meet is determined by these fusion rules here. And so in the C2 example, it basically says there has to be an even number of things coming in. So if you've got a generic cell decomposition, we're basically summing over surfaces in our three manifold. So it's a very simple state sum. And then once we have a surface, this factor here can be either even or odd. So then we're summing over, we're sort of taking a sum over two cycles in the three manifold. And then once we fix the two cycle, we take a sum over one cycles in the two manifold. And so that suggests, so that's what I've written here. And so my guess, which I'm moderately confident of, is that this invariant for the C2 theory is equal to half the sum over all Z2 homology classes, two-dimensional Z2 homology classes. Each of these can be represented by a surface, and we just take -1 to the R invariant of that surface. So, in general, if you have a very simple input category, you expect the TQFT you get out to possibly be some kind of classical invariant. And here's my guess for what it is in one case. If we were doing these more complicated things, then our surfaces would in fact be foams. We would allow three surfaces to come together, not just two. We would disallow one. But it's an interesting question whether, again, we might get some kind of classical invariant. And that is all.
Fabulous, thank you. Are there questions for Kevin?
So Kevin, in this last example, this is Eric Rowell. These last fermionic things, can you describe actions of mapping class groups on these superspaces?
Yes, and I should have said that this figure comes from a paper that I wrote with Dave Assen and Ethan Lake. And in that paper, we mostly just work out the S&T matrices for the mapping class group action for a torus. So that's worked out in full, with explicit matrices in full detail there.
Okay. And maybe as a follow-up, so if we have some points in there, some boundary, can you describe, like, what we'd expect for, the analog of braid group, et cetera?
Yeah, I think some of the braiding matrices are written down in the paper. I don't remember how much, but the construction of these categories is very explicit. We start out with a category that we know, like icing in this case, or SO3 level 6, half of E6, and then when you do the fermionic condensation process, that allows you to express all the basic data for the quotient category in terms of the parent category. So there's probably half that paper is working out explicit examples of that idea. So I think if you look there, that would give you the tools you need to do that. But we haven't. I think even though we may have written down the braiding matrices, we didn't try to say anything about braid groups in general.
Okay, thanks.
So I guess the obvious push out here is superfusion 2 categories. Any thoughts on those?
No, I had not even contemplated that push out before. So yeah, I guess there are these results most recently by David Reuter that semi-simple 3+ one-dimensional TQFTs, don't give you interesting information, and my guess is that that's also true for the super versions, but I don't think that's been done yet. So that's an interesting question. And secretly, I actually find these things interesting, even though they don't do a good job of distinguishing, four manifolds. I think they're interesting invariants myself. So.
Yeah. Any other questions? Great. Well, let's thank Kevin again, and I'll put the link to the tea room in the chat. There it is for anyone who wants to just hang out after. Thanks again.